assume that to work for now. Today we're gonna be looking at, essentially we're gonna spend the time looking at those phase diagrams for two component systems. We looked at the formulas for the chemical potential when we make solutions, when we mix one, a solute into a solvent. So we derived all of the energetic expressions for these systems last week. Now we're just going to spend the day looking at the phase diagrams. The phase diagrams run very similar, parallel to the phase diagrams for the one component systems, in that we find that when we increase pressure, we drive these things into the liquid phase. When we decrease pressure, we drive them into the gas phase. When we increase temperature, we drive them into the gas phase. When we decrease temperature, we drive them into the liquid phase. The only difference is that we're not dealing with a single component. We've got two components in our system, and it turns out that the gas phase and the liquid phases have different compositions that depend on the values of temperature and pressure. So we're going to look at that. Incidentally, we're kind of wrapping up Chapter 6 material, so the stuff that we covered today will be on the exam next week. We're going to have the exam next week. But there's not a lot of math covered today. It's mostly just qualitative stuff. So we're going to try to get you guys introduced to these two component phase diagrams and get you to a point where you can look at them and kind of analyze them qualitatively. And I won't probably have any questions that are quantitative on these two component phase diagrams, but certainly I'm going to have a qualitative question. So starting out, we go back to the ideal solutions and Raoult's law. We said that Raoult's law held for systems where the interactions between the different components in the solution were approximately equivalent. So if we have a solution composed of A molecules and B molecules, if the relative forces between these molecules are the same, then they'll obey this system, or they'll obey this law, Raoult's law, where the pressures of the gases in the gas phase, P1 and P2, will be proportional to their mole fraction and the pressure that they exert when they're in a pure liquid by themselves. So we're looking at the pressure above a liquid surface, and for these ideal systems, Raoult's law is followed. We can take Raoult's law and derive an expression for the total pressure above this system as a function of its composition. So right here, we have on the x-axis the mole fraction of a component in this solution. I've written this component as x1, and you see that there's a linear relationship between the total pressure. This line here is the sum of the pressures. There's a linear relationship between the total pressure and the mole fraction of x1. And if we just write out the total pressure as the sum of P1 plus P2, and we enter those pressures, P1 as being the mole fraction of P1 times the pressure of the pure solution, and P2 as being the mole fraction of P2, but again, the mole fraction of component 2 is 1 minus the mole fraction of x1. We sum those together and we get an expression that looks like this, where the total pressure is equal to, in this case, P2 plus M. This is a linear form. Y is equal to B plus mx, M times the mole fraction of x1. The way that we've drawn this guy, component 1 is the more volatile component. You can see that because when its mole fraction is 1, we've got the highest pressure, right? And so if this is the most volatile component, then relative to when the other one is the only component present, this pressure will be higher. P2 is the less volatile component, and when it's the only component in the solution, the pressure is lower. So we have that linear relationship between the pressure and the mole fraction. And just some notes that mole fraction of component 1 is 0. The total pressure is P2 pure. The mole fraction equals 1. The total pressure is P1 pure. What else did I want to say about that? Okay, yeah, and so obviously we want to be able to look at this graph and know what the implications were. The total pressure here is the pressure exerted by the vapor of the solution, right? So we've got a solution, it's a component, it's a mixture of two components. This is the pressure that its vapor is going to exert onto the external environment. And if we saw with the one component systems, if the external pressure is equal to the vapor pressure, then we'll have an equilibrium situation, right? And then we'll have gas and liquid existing together in equilibrium. What happens to the solution if we raise the pressure past whatever that combination equilibrium pressure is? If we make the pressure higher, if we make the external pressure larger than the equilibrium pressure of the vapor.
Is the gas going to condense the liquid?
Yeah, then we favor the liquid phase. We're pushing harder on that gas than the gas is pushing back, and so we're driving it all into the liquid phase. And similarly, if we lower the pressure below the vapor pressure of the solution, then we're going to end up favoring the gas phase because the solution is pushing out at us harder than the external environment is pushing back, and so the gas will expand against the external environment and it'll drive it all the way into the gas phase. So this is one way of looking at it. We're looking at the pressure with respect to the mole fraction of a component. Turns out this is the most volatile component in this case. The pressure with respect to the mole fraction in the liquid. We can do some math. I'm not going to show it to you because it's not absolutely necessary. You can do it later if you like. But we can do some math to express the pressure in terms of the mole fraction. This Y1 right here is the mole fraction of a component in the gas phase. So we can express the total pressure in terms of the mole fraction of a component in the liquid, or we can express it in terms of the mole fraction of the component in the gas. And in that case, we get a similar graph. I guess it might be on the next slide. We get a similar graph where we have pressure versus mole fraction, but because we now have that mole fraction term in the denominator, it changes its shape. Oh, there it is. So it changes its shape, and we get this kind of a curve here. You'll notice, though, that the two curves, whether we're plotting with respect to the mole fraction in the gas phase or the mole fraction in the liquid phase, the two curves begin and end at the same points, right? Because the pressure of the pure is going to be the same at mole fraction equals 0 and mole fraction equals 1. So these two graphs begin and end at the same points. That makes it very easy to superimpose them. And when we do, we get a graph that makes it very easy to relate the pressure of the system and the mole fractions in the various phases. So that is the graph that we're looking at here. Here we have that liquid composition line, that's the linear slope line, and the vapor composition line plotted together on the same graph. And what those do is they allow us to pick a point of pressure and to identify what the composition of the mole fraction in the gas phase will be and what the composition of the mole fraction in the liquid phase is going to be.
Is this all at room temperature?
Yeah, we're gonna touch on that in a second. So we're varying temperature. In a second, we're gonna look at the phase laws, and the phase laws tell us that we have so many variables that we need to describe our system and so many degrees of freedom. One of the variables is pressure, as we've seen here. Another is temperature. For these graphs, we're holding temperature constant. So this is a constant temperature kind of snapshot in time. And what that means is that the total thermal energy present in that vapor or in the liquid solution is kind of constant. And so the solution is pushing out with a constant pressure. It's pushing gas phase molecules out with a constant pressure. And what we're varying is the external pressure, so the pressure that we're pushing back on it with. So something to note about this graph, if you take a given value of the pressure and you draw a line between, or you connect dots between the mole fraction in the liquid phase and the mole fraction in the gas phase, in the vapor phase, what do you notice about the mole fraction of the vapor with respect to the mole fraction of the liquid? I guess that's a dumb question, I should just answer it. What I'm getting at is that the mole fraction in the gas phase is essentially enriched in the component that's the most volatile. So in this case, this X or Y that we're looking at is the most volatile component. We know that because the pressure is largest when its mole fraction is 1. But we see that relative to the liquid phase, the vapor in this case is always, we draw a line from the liquid over the vapor always has a larger mole fraction of that more volatile component. And that's important. It's going to be important for fractional distillation, which we'll look at in a second. So, from a moment in time when we're at equilibrium, let's say that we create some disturbance to the system that destroys our equilibrium, and ask ourselves what we would have to do in order to restore equilibrium based on this disturbance that we made. So, if we take a point here, x initial and y initial, and we increase the external pressure, so we start pushing down on that gas phase with more pressure than it's pushing back. We favor the liquid phase, right? We drive this guy into the liquid phase.
Mm-hmm.
What would we have to, what changes could we make to the solution that would cause the liquid phase to, or kick off more molecules into the gas phase?
Increase temperature.
Well, yeah, you could increase temperature, absolutely. But holding temperature constant and just looking at the pressures and the mole fractions, what could we do to the mole fractions to get the solution to push out with more strength?
To increase it?
Increase the mole fraction of which component?
More volatile gas.
Yeah, whichever one is the more volatile gas. And that's what I'm kind of getting at here when I've drawn these points and these points. So if we move from some lower pressure to some higher pressure, we notice that to get back to an equilibrium position, we have to move along that mole fraction curve to higher values of the mole fraction of the more volatile component. Basically, all that means is that whatever component is the most volatile, that's the one that's trying to push out from the liquid phase into the gas phase. And if we increase the amount of it there, or that's in the solution, we essentially increase the pressure, the vapor pressure exerted by that solution. So the same way that we were looking at, I guess I could draw it. Same way that we were looking at these diagrams, where we have a liquid, we have a line of equilibrium where we had maybe an equilibrium between a liquid and a gas phase. If we changed pressure, we would have to change temperature along with it. In these curves, we can think of maintaining equilibrium in the same way. If we were to alter the pressure, in this case, we could in order to keep ourselves at equilibrium, we could alter the mole fraction. But if we don't alter the mole fraction, we don't stay at equilibrium. So a change in pressure is going to push us away from equilibrium unless we make some other change at the same time. And so holding temperature constant, the only variable that's left to change is the mole fraction. And so if we change the pressure and move ourselves away from equilibrium, we can change the mole fraction and push ourselves back to equilibrium. So here, if we increase the pressure, it would favor the liquid phase, and we'd have to increase the mole fraction of the more volatile component. If we decrease the pressure, that would favor the gas phase, and we could restore equilibrium by decreasing the mole fraction of the more volatile component. Similarly, if we change the composition by adding or subtracting one component or another, we could change the pressure at the same time to move us back to equilibrium. So those observations that we made can be summarized in, or are summarized by something called the phase rule. And the phase rule tells us that for any of these systems, our degrees of freedom, the number of degrees of freedom, is equal to the number of components, C, minus the number of phases, P, plus 2. So for the systems that we just looked at, we had two component systems, right? We've got A molecules and B molecules. We have two phases, and so if you take C is 2, phases is 2, that leaves us with 2 degrees of freedom. With 2 degrees of freedom, we've got temperature, pressure, and mole fraction as our variables. If we take temperature and hold that constant, we get rid of one of our degrees of freedom. That means that we only have 1 degree of freedom left and 2 variables that are left to describe our system. And so those 2 variables have to be linked. In this case, we saw that the pressure and the mole fraction were linked at the equilibrium position. If we are going to maintain equilibrium, if we're going to keep 2 phases, then pressure and mole fraction have to vary together. If we decided that we weren't, it wasn't necessary to stay at equilibrium, that we could allow ourselves to be in the single component phases of the system, like single component gas, or sorry, not single component, single phase sections, gas phase or liquid phase. If we decided that we wanted to stay there, we would end up having 3 degrees of freedom, right? Our components is 2, our phases is 1, 2 minus 1 plus 2 is 3. Then we select temperature, so we get rid of that degree of freedom, we're left with 2 degrees of freedom. And in that case, we can vary the pressure and the mole fraction at the same time. All of that's saying is that if you have, on this graph, if you're at some point that's not at equilibrium, and you're in a single phase, I guess that was, this was liquid, this was solid. If you're in one of the single phase regions, you can change the pressure. Pressure could go down and you could move from this point to that point, or pressure could go up and you could move from that point to that point. If it wasn't required that you stay along this equilibrium line, then you can vary the mole fraction and the pressure independently and still stay in that single component region of the system. Okay? So learn how to use that phase rule. Along these lines, if we're tracing out a position on the boundary and we're moving from one equilibrium point to another where we have 2 phases in equilibrium, then our degrees of freedom drop. There becomes a requirement on the linking of those variables. Read my notes and see if there's anything else I wanted to say. reset all of that. That phase rule can be applied, I didn't mention this when I discussed single component systems, but it also applies to single component equilibria. If you look at the situation where we were tracing, or we're looking at our degrees of freedom in those in that single component phase diagram, if we're in a single phase region, so solid, liquid, or gas, our degrees of freedom, we've got one component, one phase, gives us 2 degrees of freedom. That we noticed that we could vary pressure and temperature within these areas independently. So we change pressure and change temperature at the same time and still stay in that one phase region. If we wanted to move along a boundary line where we had 2 phases in equilibria, solid and liquid, liquid and gas, liquid and solid, if we wanted to move along those boundary lines, our degrees of freedom decrease. Our components is still one component system, the number of phases is 2, so our degrees of freedom ends up being 1 degree of freedom, and that left us with a situation where any change in pressure would require a concomitant change in temperature in order to maintain equilibrium. We couldn't, along those equilibrium points, we couldn't vary pressure and temperature independently. You can also apply the phase rule to the triple point. In that case, components are still one component. We've got 3 phases. That leaves us with 0 degrees of freedom. And you notice by looking at that graph for the single component equilibria that once we're at the triple point, we can't vary pressure or temperature. We have to keep those values fixed when we move away from the triple. So you can apply that phase rule to your single component systems as well. All right. So the first graphs that we drew, we looked at pressure and mole fraction relationships when temperature was held constant. A much more useful graph is the one where we choose to hold the pressure constant. It's more useful because most chemical processes happen at a constant external pressure, not necessarily a temperature. We hold the pressure constant, and we look at the changes in or the equilibrium between temperature and mole fraction. And so, setting this graph up again the same way we did, where the mole fraction that we're varying was the mole fraction of the more volatile component, we see that it kind of inverts. It inverts the position of the vapor phase and the liquid phase change. Our liquid was up here before because as we increased temperature, we drove to the liquid phase, or as we increased pressure, we favored the liquid phase. Now the liquid phase is down here because as we drop temperature, we end up favoring the liquid phase. And the vapor phase is at the top because as we increase the temperature, we end up favoring the vapor phase. Mole fraction of the more volatile component is plotted on the x-axis, and we see that when the mole fraction goes to 1, the temperature necessary to maintain equilibrium drops. Because it's the more volatile component, it's already trying to escape into the gas phase, and therefore a lower temperature is requisite to keep that pressure at wherever it needs to be, to keep the liquid pushing out. So this guy inverts. Again, we can apply the phase rule. The number of degrees of freedom is components minus phases plus 2. Along those boundaries, we have 2 components, 2 phases, so we have 2 degrees of freedom, but we've got fixed pressure, so we have 1 degree of freedom left, which tells us that in order to maintain equilibrium, any change in temperature is going to require a concomitant change in the mole fraction, right? So you increase the mole fraction, or you increase the temperature, of something, what does that tend to do to the vapor, the pressure of the vapor?
Increase it?
It's going to increase the pressure of the vapor. So if we move from one point here to a point up there, what are we going to have to do to the mole fraction in order to maintain equilibrium?
Going from where to where?
So let's. I should have drawn this out a little more carefully. But if we're at a point here where we've got equilibrium, this is showing at a given temperature, we've got a mole fraction x1 in the gas phase, or so the liquid phase, and mole fraction y1 in the vapor phase. If we're at that point of equilibrium and we increase the temperature, it's going to start to favor the gas phase, right?
Mm-hmm.
Assuming that this is the molar volatile component that we're plotting here on the x-axis, what will we have to do in order to move back to an equilibrium position?
Decrease the...
We have to move backwards on this line, right? We've got to come this way. We've got to decrease. The more volatile component is pushing out into the gas phase, and so if we decrease its mole fraction, the net push into the gas phase decreases. And so an increase in temperature on this graph would require a movement that way on the x-axis, a decrease in the mole fraction of that more volatile component in order to maintain equilibrium, right? A decrease in temperature, we're not pushing as hard, or we're not pushing molecules as energetically out into the gas phase. And so if we decrease the temperature, we end up requiring an increase in the mole fraction of that more volatile component to maintain equilibrium, right? So if we drop temperature down, we've got to move in that direction. So down here, just got a summary of the different changes that we can affect on the system and what changes we would have to then make in order to favor or in order to restore equilibrium. So an increase in temperature pushes us towards the gas phase. We'd have to lower the mole fraction of the more volatile component to maintain equilibrium. A decrease in temperature ends up favoring the liquid phase. We'd have to raise the mole fraction of the more volatile component to maintain equilibrium. If we change the components, there would be similar changes in temperature that would be requisite to maintain that equilibrium position. So all of those graphs that we looked at, well, actually, before I get into that, let's talk about fractional distillation. So going back to these guys, we can use these curves to argue for the results or the phenomena of fractional distillation. Let's say that you have a system that is at a given point. Let's draw a line here and say we're at point A where you've got some composition of the liquid phase. And you pick that point, and you raise the temperature to some value until you've reached a point where vapor and liquid are in equilibrium. You now separate the vapor and the liquid from each other. You look at their relative compositions. What's the difference in the and the composition of the liquid and the vapor. What happens to the, oops, I drew that guy backwards. This way.